Okay, so here we're going to talk about the calculus of inverse functions. And we're going to start with introducing these two theorems. The first we'll just state without proof, and then the second one we'll dive a little deeper and derive the proof here. The first one states that if f is one-to-one and continuous on an interval, then its inverse, f inverse, denoted by that notation, is also continuous. Now here you can think of graphically that does make sense if we think of the graph of a function f. If it is one-to-one on a given interval, then it has an inverse. And the graph of that inverse can be found by just reflecting it across that line y is equal to x. So it makes sense that the reflection is also continuous. Again, if f is also continuous. All right, now let's take a look at the next one, because this one does have an implication in terms of calculus where, well, let me go ahead and just read it, right? If f is one-to-one and differentiable with inverse function, f inverse, and this is f prime, so this is the function f, the derivative of f, and, excuse me, f prime of a not equal to 0. All right, here, let's place the parentheses here. Okay, so the derivative of the function value of the inverse at a is non-zero, then the inverse function is differentiable at a. And the derivative of the inverse at a is equal to 1 over the derivative of the function value of the inverse of a. Now let's take a look here graphically what this means here. All right, so if we see here we have two functions, right? We have the f and the f inverse, and this line here is y equals to x. Okay. All right, and if we're finding the derivative, so here what we're after is what is the derivative, or in other words, the slope of the tangent line at a, right? And if we're kind of reflecting it, if the graph is a reflection across the line y equals to x, so what we know about inverses is that their domain and range are kind of flipped around here, right? So here if you see this delta x, notice that along here, this value of delta x in the red here is the value along the vertical for the f, right? And then vice versa, right? The delta y here is the value along the horizontal here, right? And this point AB on the inverse is actually the point BA on the function f. So if we're trying to find what is the value of the derivative at a point A, then what this is telling me really, I don't actually need to go through the trouble of finding the derivative of the inverse function, right? If all I'm looking for is the value at a particular point, it is enough to find the derivative of f, right? And then at the point AB here, right, find the value of what is f prime of b essentially, right? Because again, what did we find out here? If we have f of b, if f of b is equal to a, then f of a, excuse me, f inverse of a is equal to b. All right, that's just the definition of inverse function. So what this is saying is you can essentially find the derivative of f, right, evaluate it at that point b, and then just take the reciprocal of it, right? And then find the value of the derivative of the inverse, right? So I don't even need to go through the trouble of finding an inverse and then taking the derivative of that, right? So here, let me work through, first of all, the proof of such theorem here. So for our proof, here we let f of b, so we'll start with that. F of b is equal to a, and again, this is if and only if, right, by definition of inverses, the inverse, f inverse of a is equal to b. All right, and then we'll let y, our function, is the f inverse function of x, right? And that means that f y is equal to x. All right, and by assumptions here, we know that f is differentiable, right? That's our theorem is one of the hypotheses, right? So if f is differentiable, then that implies that f is continuous. So f is continuous. Now be careful how you interpret that. The inverse is not true. Right? Continuity does not imply differentiability, but differentiability does imply continuity. Okay? So if f is continuous, then our first theorem up here tells me, right, well, f inverse is also continuous. Okay. So that means that based off of this logic here, f inverse is continuous. Okay. All right. And then furthermore here, let's say then that implies that as x, if it is continuous as x approaches a, right, then the f inverse of x approaches the function value of a, right? And that just comes from continuity at a point, right? Okay. So if this is true, then what that means is that we define y to be equal to b. Excuse me here, where did I have that here? Oh, excuse me, f inverse of a to be equal to b, and f inverse of x to be y as y approaches b. Okay, so now as we kind of got the notation here, then we could say, all right, let me set up my limit, right? So here, we want to use the limit definition of the derivative, right, to prove that this converges to the value that we have up here. Okay, so we start with the limit as x approaches a of f inverse of x minus f inverse a, and then x minus a. Okay, and then here doing some substitution of what we have up here, we could say, right, so as x approaches a, then these other quantities hold true. So I'm going to rewrite this, doing some substitution to arrive at my conclusion, right? So I'm going to change, as x approaches a, right, then y approaches b. So I'm just going to switch that out. Y approaches b. And then on top we have y minus b. And then down here we'll have f of y, which is my a, minus f of b. All right, and again, these are just substitutions from the above logic here. Okay, all right. And now just using the reciprocal here, I can rewrite this as 1, so I'll bring the limit in the denominator and then rewrite this as a complex fraction. The limit as y approaches b of f of y minus f of b over y minus b. All right, and we know that this limit exists, right? So this means because f is differentiable, right? That was part of our assumptions. So that is f prime of b. So it converges to that, but b, again, as above, b is f inverse of a. And that gives us our conclusion for the theorem, the f inverse of a. All right, as long as this quantity is non-zero. Excuse me here. Okay. All right, so again, derivative, inverse. Okay, so now let's do an example to kind of look at how this is going to be used in an application here. Okay, so for an example, oops. Okay, so an example here. Okay, so we let f of x equal to square root of x. Oh my God. Plus x squared plus 1. All right, so this function is 1-to-1. So we're told that it is in fact 1 1-to-1 for values of x bigger than 0. So we restricted the domain, which is allowed, right? If a function is not 1-to-1, then we can allow to restrict the domain so that it is in fact a 1-to-1 function. All right, and this will make it a 1-to-1 function. So that means that it has an interval, right? Has an inverse, excuse me. In that interval. Okay, so I want to find the slope, or in other words, the derivative, right? Find the slope of the tangent for the inverse for y equals to f inverse of x at the point 3, 1. Okay, so this is my problem here that I have. Okay, all right. So one thing to recall, a couple things here. So this point here, this is on the inverse, right? On the curve f inverse of x. So what that means is that if 3, 1 is on the inverse of x, then that means that 1, 3 is on the curve f of x. Okay. All right. In other words, what this means that f of 1 is equal to 3. All right. If and only if, right, that implies that f inverse of 3 is equal to 1. Okay, and what I'm tasked to find is I want to find the value of this. Okay, now if I didn't have the theorem above, I would start by trying to find the inverse, then take the derivative of that, right? But looking at our function, that looks rather challenging. We have a squared and a square root. If we look at our function here. So I'm not going to do that. And I'm not going to find an inverse, right? I'm going to, this theorem that I have, excuse me, this theorem that I have out here allows me to bypass that. Okay, so instead what I'm going to do is I'm going to find the derivative of f, right? That I can find. Right, pretty straightforward here. f prime of x is equal to 1 over 2 root x plus 2x, right? Again, using the power rule, the constant just becomes 0. All right. And what I'll do is I will plug in the value at 1. All right, so at 1 we get 1/2 plus 2, so now we get 5/2. Okay, so now applying the theorem that we had above, the derivative of the inverse at 3 is equal to 1 over f prime of the value of the inverse at 3. So the value of the inverse of 3 is 1, right, from the definition here, right? F inverse of 3 equals to 1. So now going back down here, we get 1 over f prime of 1. And I just calculated that above. So that's 1 over 5/2, which reduces to 2/5. Okay, and there we go, right? Notice I did not have to find an inverse, which really helped me out here, right? I just needed to, as long as it satisfied the above conditions, which were, right, f is 1-to-1 and differentiable with an inverse function, and the derivative is not equal to 0, then I was able to calculate a derivative of an inverse function without having to find the inverse, which was very helpful here.